Chapter 9 discusses alkynes. The learning objectives for this video are an overview of alkynes, including how to name them, how to prepare them, what happens when you react them with HX or X2, where X is a halogen, and then also I'll show you some hydration reactions involving alkynes. Alkynes are molecules that possess a carbon-carbon triple bond, and the carbons are sp hybridized. So they have two sp hybrid orbitals, and they have two unhybridized p orbitals. The sp hybrid orbitals are involved in forming the sigma bond. So the carbon-carbon triple bond is composed of one sigma bond and two pi bonds. The sigma bond is formed from an overlap of the carbon's sp orbitals. So each sp orbital on the carbons attached to each other overlap to form the sigma bond. Then the two pi bonds are formed from the overlapping unhybridized p orbitals. So each carbon has two unhybridized p orbitals that overlap to form the two pi bonds. So these dotted lines are showing that those orbitals are overlapping, even though it doesn't look like it in this picture. Due to the presence of the pi bonds, alkynes are nucleophilic in a way that's similar to alkenes that we saw in Chapter 8. And indeed, many of the reactions that worked with alkenes also work with alkynes. Alkynes are prevalent in industry and in nature. Acetylene is the simplest alkyne. That's just a carbon-carbon triple bond. It's used in blowtorches and as a precursor for the synthesis of more complex alkynes. There are more than 1,000 different alkyne natural products that have been isolated. An example shown here is that of histrionicotoxin, and that is a toxin found in the skin of poison frogs, which are located and native to Colombia. It is likely that, as with other poison frogs, these histrionicotoxins are not manufactured by the amphibians, but absorbed from insects in their diet and stored in glands in their skin. This toxin acts as a neurotoxin, and it inhibits nicotinic acetylcholine receptors. And this video here is of a poison dart frog from Colombia that has this type of toxin. Ethynyl estradiol is an example of a very important synthetic alkyne. It is an active ingredient in many birth control pills. Naming alkynes is similar to how we have named other alkanes and alkenes. First, you identify the parent chain, which must include the carbon-carbon triple bond. Then you identify and name the substituents. You add a locant and prefix if necessary, giving the carbon-carbon triple bond the lowest possible number. Then you arrange everything in alphabetical order, and then you place the carbon-carbon triple bond locant either before the parent name or just before the YNE suffix. So you first identify the parent chain, which is the longest carbon chain containing the triple bond. So here the parent chain would be heptyne 1, 2, 3, 4, 5, 6, 7, because that's the longest chain that includes the triple bond. Compare that to an alkane, where octane would have been the parent chain. Now the substituents here, this is a 3-carbon substituent, so that would be propyl. Just like with alkenes, you're going to number from the end that gives the triple bond the lowest possible numbers. So here you would number from the left. This would be incorrect. And the locant will be, that's just the number, that will be the number of the first carbon of the triple bond. So it would be 2. Now when we put this all together, we note that there are 2 methyls at carbon 5 and a methyl at carbon 6. So this entire structure becomes 5,5-trimethyl 2-heptyne. Alternatively, you could put the 2 before the suffix YNE. Alkynes are prepared from geminal or vicinal dihalides. A geminal dihalide is a compound that has 2 halogens on the same carbon. So these bromines are both attached to the same carbon, so it's called a geminal dihalide. A vicinal dihalide has two halogens attached to neighboring carbons. So either one of these, if you treat them with a strong base like hydroxide, you will end up with the alkyne. And this occurs through a mechanism that we're going to learn in a subsequent chapter. It's called the E2 mechanism. Hydrohalogenation, like we saw with alkenes, also works with alkynes, and it also affords Markovnikov addition of H and X, where H goes to the carbon with more H's and X goes on the other carbon of the alkene. Now, if we just added one equivalent, we would get to this product. But typically what is done is you add an excess of HX to get to a geminal dihalide. So essentially it adds twice. So when it adds once, you get the alkene compound, and then when it adds again, you get the geminal dihalide. Now the mechanism, if it was analogous to that we saw with the alkene, it would require the formation of a vinylic carbocation. That's where you have a positive charge on a sp2 carbon. That is unusually unstable, so this mechanism is probably not likely. Kinetic studies have been done which suggest that the rate law is equal to the concentration of the alkyne times the concentration of HX to the second power. That means that in the slow step, there are 2 molecules of HX involved and 1 molecule of the alkyne. So a proposed mechanism is shown on this slide, where you have the pi bond attaching to the hydrogen, breaking the HX bond, and then a second HX molecule donating an X to the other carbon of the alkyne, which gets you to this vinyl halide, which could then go on and react with more HX to give you the geminal dihalide. It is possible that there are several competing mechanisms occurring. Reacting an alkyne with a halogen, such as chlorine or bromine, will give what's called a tetrahalide. So that's where you have 4 halogens attached to neighboring carbons. So the triple bond has transformed into a single bond, and you've now added 2 bonds to the halogen on each of those carbons. Alkynes can also undergo acid-catalyzed Markovnikov hydration. In this, HgSO4 is typically used to speed up the reaction, and you form what's called an enol intermediate, which is not isolated but tautomerizes to the ketone. So in this mechanism that is shown in your textbook, the triple bond acts as a nucleophile attacking the mercuric ion, forming this intermediate. Now, I just said that these vinyl carbocations aren't very stable, and they're not. So in reality, the actual mechanism isn't as simplified as this, but this is how it's generally presented at this level. Then the water is going to attack the positively charged carbon, and you get to this intermediate, which then undergoes a proton transfer to get you here. Then a proton is going to replace the mercuric atom. So the pi bond attacks the H of H3O plus to form another carbocation, which is stabilized through this resonance. And then the mercury leaves as mercury 2 plus to deliver this enol. And this is called an enol, En for the carbon-carbon double bond and OH for the alcohol. The enol then tautomerizes to the ketone through a process called keto-enol tautomerization. The enol and ketones are tautomers, and the equilibrium generally favors the ketone. So tautomers are just isomeric compounds that can rapidly interconvert by the movement of a proton. And these would be constitutional isomers because there are different functional groups and the atoms are connected in a different order. So here we have an alkene and an alcohol. Here we have a ketone functional group. And the ketotautomer is favored because the carbon-oxygen double bond is stronger than a carbon-carbon double bond. Now, when you hydrate an unsymmetrical alkyne, you will get a mixture of products. So if the R group here and the R group here are not the same, you will get a mixture. Because the OH will add in some reactions on this carbon and another on that carbon. Since neither carbon has an H, then there is no selectivity for the H going on the carbon with more H's. Now, if you have a terminal alkyne, you will only get one product, and it will be a methyl ketone. So here, this is the carbon with more H's, so the H always goes on that carbon and the OH on the other carbon. So when you add water to this, you get H on the carbon on the right and OH on the carbon on the left, which is your enol, which tautomerizes to the ketone. You can also perform hydroboration oxidation on alkynes using BH3 or some other similar borane reagent. This reaction also produces an enol which tautomerizes to the ketone or the aldehyde, depending upon whether you started with an internal alkyne as shown here or a terminal alkyne. So the terminal alkyne, which is an alkyne where the carbon is attached to a hydrogen, one of the carbons of the alkyne is attached to a hydrogen, it will give different products depending on whether you do the mercury 2 catalyzed hydration or if you do a hydroboration oxidation. With this set of reagents, you get the methyl ketone. With this set of reagents, you get an aldehyde. So why is that? That's because with the mercury 2 catalyzed hydration, the H goes on the carbon with more H's. It follows Markovnikov. So the H goes here and the OH goes on the other carbon, which then tautomerizes to the methyl ketone. With the hydroboration, it's the opposite. The H goes on the other carbon and the OH goes on the less substituted carbon to give you that enol, which tautomerizes to form an aldehyde. Now test your understanding. Which of the following statements best describes the general reactivity of alkynes? Look at the options and put your answer in the chat. Question 2. What is the name for the molecule shown here? You have options A through E. Select your option and put your answer in the chat. Now this question is asking you to predict the product. So we have a terminal alkyne and we're doing a mercury 2 catalyzed hydration. So remember, this is going to go through an enol intermediate which will tautomerize to the final product. So what do you think is the final product here? Now we have a similar reaction but a different starting material. Again, we have a terminal alkyne because this carbon of the alkyne is attached to a hydrogen, not another carbon. We're using the same reagents as the last reaction. Which product would you get from this? Now here we are going to use 9-BBN, which is a borane type reagent that works just like BH3. And then we're following it up with an oxidation step. So this is a hydroboration oxidation reaction. We have a terminal alkyne. And which of the products shown will you get with this? Put your answer in the chat. So of the reactions discussed in this video, which involve the formation of an enol intermediate? Hydroboration oxidation, mercury 2 catalyzed hydration and dilute sulfuric acid, hydrohalogenation, both A and B, or both A and C. Now here's a reaction involving an alkyne and reacting it with excess chlorine. Carbon tetrachloride is just the solvent, so it won't be reacting. Which product would you get from the choices shown? And finally, we have a terminal alkyne and we're reacting it with excess HCl. Which product would you get? Remember, this follows Markovnikov's rule.